Hello everyone, welcome to the class U18 PCAE 601 Finite Element Analysis. Myself, Mr. N. Kalaimani, currently working as Assistant Professor in the Department of Aeronautical Engineering, Bharat Institute of Higher Education Research, Chennai. Today we are going to discuss the topic of static analyzing beams by finite element analysis. So before entering to this topic, I would like to recall some fundamentals of structural mechanics. Means the force that act in a body can be divided into two primary types. One is applied force, another one is reactive force. If it is a applied force, it means the force directly applied on the structures, maybe it is a dead load or live load. If it is a dead load, means the load does not vary with respect to time. If it is a live load, the load is vary with respect to time. If we consider a building structures, inside the building, the people are moving around the building. Therefore, the load is keep on vary with respect to time. Then it is called as a live load. Then the reactive forces are forces generated by the action of one body on another and against typically occur at connection or supports. The existence of reactive forces follows from Newton's third law, which states that for every action there is an equal and opposite reactions. Then what is mean by supports? Supports are basically provide base or foundation to the structures. It will restrict the movements of the structure under the influence of reactive forces. Therefore, the loads acting on the structure, it will try to move the structure, but the support will be offer some reactive forces. The reactive forces will be restrict the movement of the structure to keep the structure in equilibrium positions. For two-dimensional structures, the supports are classified. One is roller support, another one is hinged support, and third one is fixed support. If it is a roller support, means the support may be placed in vertical, horizontal, or inclined. It will offer reactive forces perpendicular to the surfaces. Therefore, it will restrict the movement that particular direction only. Therefore, the degree of freedom for roller support is 2. Then hinged support, it will offer two reactive forces. It will restrict the movement of the structures in two directions, but it is allows free to rotate. Therefore, the degree of freedom for hinged support is 1. If it is a fixed support, therefore it will offer two reactive forces as well as one moment. Therefore, the translation in two direction as well as rotation also restricted. Therefore, the fixed support having 0 degree of freedom. Then what is mean by beam? Beam is a structural members. It will subject to transverse loading. That means the load is perpendicular to the beam axis. It will resist the applied loading by combination of internal shear force as well as bending moment. It is the most widely used structural members. It can be classified based on the support and conditions. One is a cantilever beam. It means the beam is one end is fixed, another end is free. Then simply supported beam. The support will be acting at the end of the beam. If it is a overhanging beams, the support will be acting before the ends. So the first three cases beam is called as a statically determinate structures. So I already told that what is mean by statically determinate structure as well as statically indeterminate structure. If the structure is statically determinate, then the internal force and reactive forces can be analyzed with the help of static equilibrium equation alone. Then it is called as a statically determinate structures. The first three cases, if a cantilever beam, the one end is fixed, therefore it will offer two reactive forces, one moment. Therefore, the number of unknowns is 3. The available static equilibrium equation for two-dimensional structure is 3. Therefore, this structure is called as a statically determinate structures. If it is simply support beam, one end is subject to a hinged support, another one is a roller support. The hinged support offer two reactive forces as well as a roller support offer one reactive forces. Therefore, the unknown is to be 3. Then this structure also statically determinate structures. Then fixed beam is, it means the both end of the beam is fixed. Each end fixed support offer two reactive force, one moment. Therefore, each fixed end will be having 3 unknowns. The total unknown is to be 6. But available equilibrium equation is only 3. So, if you want to analyze this type of structure, in order to, we have to develop additional stress and compatibility equation to solve this kind of structures. Therefore, the fixed beam as well as continuous beam is having statically indeterminate structures. The continuous beam means the beam having more than 2 support, then it is called as a continuous beam. We try to formulate a finite element equation for beam element. So if you want to formulate your finite element equation, then we have to derive the shape function for beam element. So I already told that the shape function is nothing but it is a mathematical expression. It will tell us how the field variable varies inside the element. Let us consider beam having a length L with a uniform cross section A throughout the length of the beam as shown in figure. The beam element consists of two nodes, each node having two unknowns. One is lateral displacement, another one is rotation. Initially, we assume the beam is to be axially rigid. Therefore, there is no displacement in horizontal directions. Therefore, each node having two unknowns, the beam element having two nodes. Therefore, the total number of unknowns is to be 4. Therefore, the degree of freedom for beam element here is 4. Therefore, the size of the stiffness matrix is 4 cross 4. So I have tried to define the displacement coefficient with the 4 unknown coefficient. P of x equal to a1 plus a2x plus a3x square plus a4 x cube. It is equation number 1. It consists of 4 unknowns. That is 4 unknown coefficient is a1, a2, a3, a4. Therefore, if you want to solve this equation, we need 4 boundary conditions. What are the boundary conditions? At x equal to 0, where the lateral displacement v equal to v1 as well as slope dv by dx equal to theta 1. The same way when x equal to L, the lateral displacement is v equal to v2 and slope dv by dx equal to theta 2. Now apply your first boundary condition when x equal to 0, then v equal to v1 into equation number 1. We will get v1 equal to a1. Similarly, we apply this second boundary condition when x equal to 0, then dv by dx equal to theta 1. That means equation 1 differentiate with respect to x, dv by dx equal to a2 plus 2a3x plus 3a4 x square. In that equation, we have to apply the boundary condition. It means x equal to 0, then we substitute the dv by dx equal to theta 1. We obtain theta 2 is equal to a2. What is our third boundary condition? When x equal to L, the respective lateral displacement v equal to v2. Then we apply, we will get equation number 2. That means v2 by L square minus v1 by L square minus theta 1 by L equal to a3 plus a4 L. This is equation number 2. Then apply your fourth boundary condition. When x equal to L, the slope dv by dx equal to theta 2. Then we will get equation number 3. That is equation number 3. Theta 2 by L minus theta 1 by L equal to 2a3 plus 3a4 L. This is equation number 3. While solving equation 2 and 3, then we will get the value of a4 and a3. We already find out the value of a1 and a2. Now I find out all the value of unknown coefficients. Then we have to substitute in the given equation 1. That means v of x equal to a1 plus a2x plus a3x square plus a4 x cube. Then we have to substitute all the values into equation 1. Then finally we arrive v is equal to 1 minus 3x square by L square plus 2x cube by L cube times v1 plus x minus 2x square by L plus x cube by L square theta 1 plus 3x square by L square minus 2x cube by L cube v2 plus minus x square by L plus x cube by L square into theta 2. If you compare with that equation v equal to n1 v1 plus n2 theta 1 plus n3 v2 plus n4 theta 2. Into above equation, we came to know that n1 equal to 1 minus 3x square by L square plus 2x cube by L cube. Similarly, n2 is equal to x minus 2x square by L plus x cube by L square. n3 is equal to 3x square by L square minus 2x cube by L cube. And n4 is equal to minus x square by L plus x cube by L square. These are called as a shape functions. Therefore, if property of shape function at their own nodal location, the shape function will be unity. In this case, we consider beam element when x equal to 0, except the shape function n1 is to be unity, other values also are zeros. The same x equal to 0, then the partial derivative of shape function n2 with respect to x is to be unity, other partial derivatives all are equal to 0. The same way, when x equal to L, the shape function n3 is to be unity, all other shape function values to be 0. At that same location, the partial derivative of shape function n4 with respect to x is to be unity, all other it will be 0. The shape function for beam element is called as a Hermite shape functions. Once you derive the shape function, then we have to derive the stiffness matrix for beam element. Maybe we can use Galerkin approach, or maybe we go for strain energy concept. So if beam is a structural member, therefore we can easily formulate the strain energy approach. Therefore, in this lecture, we will go along with the strain energy concept. The strain energy for a beam element is given by U is equal to 0 to L m square by 2ei into dx, where m is nothing but bending moment. It will define m equal to ei into d square v by dx square. This formula you already studied in strength of material. That we substitute in the strain energy equation, we arrived u is equal to ei by 2 0 to L d square v by dx square the whole square into dx. We know the displacement function v is equal to n1 v1 plus n2 theta 1 plus n3 v2 plus n4 theta 2, where n1, n2, n3, n4 called as a safe function. It is a function of x. Therefore, if you want to double derivative of this lateral displacement, we will get d square v by dx square equal to d square n1 by dx square times of v1 plus d square n2 by dx square times of theta 1 plus d square n3 by dx square times of v2 plus d square n4 by dx square times of theta 2. Then we substitute into above equation in the arranged in matrix form. Then we will get d square v by dx square to b times of del, where del is nothing but a displacement vector function. Then b is called as a function of d square n1 by dx square, d square n2 by dx square, d square n3 by dx square, d square n4 by dx square. And how we will find out d square n1 by dx square? We already find out the safe function annual value in terms of x. Then we have to differentiate that equation into 2 times. Then we will get d square n1 by dx square. Therefore, if you want d square v by dx square, then we get b matrix into del the whole square. That will be reference here. Del transpose b transpose into b into del. Then we have to substitute in the above equation. Finally, we arrived where strain energy equation U is equal to E by 2 0 to L del transpose b transpose matrix b into del times dx. We know that strain energy equal to 1 by 2 del transpose k times into del. Where comparing equation 1 and 2, we will get the stiffness matrix, where the stiffness matrix k is equal to ei 0 to L b transpose times into b into dx. We know that b transpose and b matrix. Then we have to substitute this above equation. Then finally we get stiffness matrix. So in this stiffness matrix, we arranged b transpose and b we multiple with, we will get one matrix where b1 equal to d square n1 by dx square, b2 is equal to d square n2 by dx square. Similarly, b3 is equal to d square n3 by dx square and b4 equal to d square n4 by dx square. Then we try to find out d square n1 by dx square. Then we have to substitute this equation. Then we will get your final stiffness matrix. It is a simple integration only. We can try to do this. So we know that the safe function n1 value, then we have to differentiate with respect to 2 times, then we will get d square n1 by dx square. Similarly, we have to calculate all d square n1, d square n2 by dx square, d square n3 by dx square, the same way d square n4 by dx square. This term is d square 4 by dx square, not d square n2 by dx square. Then we will obtain b1 square values. Then we have to integrate 0 to L b1 square times of dx. Then we will get 12 by L cube. These are the simple integration only. You can do it yourself. Then we have to find out 0 to L b1 into b2 times dx. We already know that value of b1 is a d square n1 by dx square value. Then b2 is a d square n2 by dx square value. We have to substitute. Then we have to integrate. Then we obtain 6 by L square. Similarly, we have to obtain all the values. Then finally, we arrive stiffness matrix for beam element k is equal to ei by L cube, matrix of 12, 6L minus 12, 6L, 6L, 4L square minus 6L, 2L square minus 12 minus 6L, 12 minus 6L, 6L, 2L square minus 6L, 4L square. This is a stiffness matrix for beam element. A beam element consists of 2 nodes, each node having 2 unknowns. Therefore, the total unknown is to be 4. Therefore, your size of the stiffness matrix is 4 cross 4 for a beam element. Then we have to formulate your finite element equation. We know the finite element equation k into del equal to your force matrix. We already derived the stiffness matrix. If you consider beam element having 2 nodes, each node having 2 unknowns, what are the 2 unknowns? One is a lateral displacement, another one is rotation. That means v1 theta 1. The node 2 is v2 theta 2. Therefore, we have to write your displacement vector function is v1 theta 1, v2 theta 2. is equal to your force is will be node 1 having the internal shear force F1 as well as bending moment is M1. Similarly, F2 as well as M2. Then this is your finite element equation for beam element. Then suppose if we consider a truss element, the load only acting at the joints, but in case of beam element, maybe it is subject to be a uniformly distributed load. Therefore, in this case, we have to form the usual approach only. It means that the distributed load, it will be converted into equivalent nodal force as well as moment. Then how we will do this such that the mechanical work done by the load of the system must be equal to work done by the distributed load. We know the work done equation, W is equal to 0 to L. The distributed load is to be Q of X times your displacement is V of X into dx. That will be references here. F1 Q, it will indicates the force at node 1 due to distributed load. In times of your lateral displacement V1, then distributed moments is M1Q times of theta 1. That is the same like node 2, F2 into V2 plus M2 times into theta 2. Where here Q is uniformly distributed load or uniformly varying load. If it is a uniformly distributed load means the load will be constant along the length of the beam. If it is a uniformly varying load, the load is keep on varying with respect to position. That means distance. That means your Q of X is vary with respect to position or distance. Therefore, it is a function of X. Here we consider as a simply supported beam. We is subject to a uniformly distributed load. Then we have to find out the equivalent force at nodes 1 and 2. The same way equivalent moments at node 1 and 2. Therefore, the above equation W is equal to 0 to L Q of X into V of X equal to 0 to L Q of X, where V of X is a N1 V1 plus N2 theta 1 plus N3 V2 plus N4 theta 2 into dx. We compare with the above equation, then your distributed force at node 1 F1Q is equal to 0 to L integral of Q of X into N1 times dx. Then M1Q is equal to 0 to L Q of X times N2 times into dx, where F2Q is equal to 0 to L Q of X into N3 times dx. Then M2Q is equal to 0 to L Q of X into N4 times into dx. The right answer, if we see that the beam is subject to uniformly distributed load, where Q is constant over the length of the beam. Therefore, in this equation, F1Q is equal to 0 to L, where Q is constant, into N1, where N1 is a same function, it is a function of X. Therefore, you have to substitute N1 value, then we have to integrate. In this case, where uniformly distributed load is constant, we taken outside of the integration. Then we have to integrate with respect to N1, then we will get the distributed nodal force at node 1. F1Q value is equal to QL by 2. In case if you want to distributed moment, then we have to M1Q is equal to 0 to L, where Q is constant for uniformly distributed only. Therefore, we take in outside of integration, then we have to integrate with respect to X of your N2 function, then we will get M1Q is equal to QL square by 12. That means it will produce a anti-clockwise movement at nodal location 1. So here we are assuming the anti-clockwise movement is to be positive, as well as the upward force is to be positive. If we consider say F2Q, the same way 0 to L Q of X into N3 times dx. If it is a uniformly distributed load, then Q is to be constant, then we have to take in outside of integration. Then the integral with respect to N3 with respect to X, we will get F2Q. Similarly, we have to find out M2Q also. That is to be a clockwise movement. That's why I mention here negative psi. Then this is equation is will indicates whenever if the beam is subject to any distributed load, then we try to convert this distributed load into nodal forces as well as nodal moments. Suppose if we consider a beam is subject to uniformly varying load, where the one intensity is 0 at one end, other end it is subject to a maximum intensity. In this case, your Q is a function of X. That means your Q of X equal to Q times X by L. Therefore, you have to substitute this F1Q is equal to 0 to L, where the Q of X is to be a function of X. It means your uniformly intensity load at a higher end. That means Q times X divided by L. Then your N1 also function of X. Then we have to substitute. Then again you have to integrate. We have to find out your distributed force as well as distributed moments. Then we have to calculate your bending stresses. We know the theory of simple bending equation. With this, we already studied in strength of material. That means M by I is equal to sigma B by Y, where Y is nothing but distance from the neutral axis. Therefore, we get sigma B is equal to M by I times into your Y, where M is a bending moment. We already know the bending moment equation EI into d square V by dx square. Then we have to substitute in this equation where d square V by dx square equal to d square n1 by dx square times of v1 plus d square n2 by dx square times of theta 2 plus d square n3 by dx square times of v2 plus d square n4 times of dx square into theta 2. The maximum bending stress occurs outer surface, as well as we need to calculate only the stresses value at the cross section corresponding to the nodal location only. Maybe a beam element is discrete to convenient number of elements. That the initial location x equal to 0, the other end will be specified x equal to L. Therefore, we have to substitute this above equation where sigma b is equal to x equal to 0. Then how we arrive this equation? Then we know the shape function value n1. That n1 we have to differentiate 2 times. We will get d square n1 by dx square. At that equation, we have to substitute x equal to 0. Finally, we will get the bending stress where the position x equal to 0 is equal to E times y max into 6 by L square times V2 minus V1 minus 2 by L times 2 theta 1 plus theta 2. Similarly, when x equal to L, that means the above bending stress equation, we have to differentiate N1, N2, N3, N4 2 times. We have to substitute that above equation, and that equation we have to substitute x equal to L. We will get the bending stress equation when x equal to L, E y max into 6 by L square times of V1 minus V2 plus 2 by L times 2 theta 2 plus theta 1. Now we derive the finite element equation as well as bending stress formula. We try to solve some numerical problems. What is the problem number 1? For the beam loaded as shown in figure, determine the slope at nodes and vertical deflection at the midpoint of the distributed load. If you look at the one end is fixed, another end is to be subject to a roller support. In between, one roller support is there. Therefore, we try to formulate a finite element equation for individual element. Then we have to assemble. We will get a global finite element equation. Now, let the beam is divided into 2 elements, 1 and 2 having nodes 1, 2, 3. Where node 1 having the lateral displacement V1 as well as rotation theta 1, node 2 having V2 T2. Similarly, node 3 will having V3 T3. We can see that element 2 is subject to uniformly distributed load. Therefore, we have to calculate the distributed force as well as distributed moment at a nodal locations. If we consider element number 1, we try to find out the element stiffness matrix value. Then K1 is equal to your Young's modulus value is already specified. What is your values? This beam is specified. E is equal to 200 gigapascal, as well as your moment of inertia is equal to 4 into 10 power minus 6 meter power 4. Then we have to substitute this value into an equation where E is equal to 200 into 10 power 9 Newton per meter square, as well as moment of inertia I value is 4 into 10 power minus 6 meter per 4 divided by length of the beam is 1 meter cube. Then where we have to substitute L equal to 1, then we will get your first finite element stiffness matrix. There were K1 equal to 8 into 10 power 5, 12, 6 minus 12, 6, then 6, 4 minus 6, 2, then 12 minus 6, 12 minus 6, 6, 2 minus 6, 4. The top we have to mention that red color that will be indicates your displacement as well as rotation of your particular nodes. If we consider element 1 consists of node 1 and 2, node 1 having 2 unknowns, that means lateral displacement as well as rotation, it will specify V1 theta 1. Similarly, node 2 V2 theta 2. Next, we have to develop element stiffness matrix for element number 2. We know the element stiffness matrix formula, then we have to substitute EI value. The same element 2 also having length of 1 meter. Then we have to apply, then we will get K2 is equal to 8 into 10 power 5, 12, 6 minus 12, 6, 6, 4 minus 6, 2, minus 12, minus 6, 12, minus 6, 6, 2, minus 6, 4. You see that the element 2 consists of node 2 and 3. Therefore, node 2 having 2 unknowns, that is a lateral displacement as well as rotation. Similarly, node having two unknowns, the lateral displacement as well as rotation. That is V3 theta 3. Then the top I reference a V2 theta 2, V3 theta 3. Now you have to assemble equation 1 and 2. Equation 1 indicates the element stiffness matrix for first element. Equation 2 indicates element stiffness matrix for element 2. Then we have to assemble, we will get global stiffness matrix. Then how we will get your global stiffness matrix? If we consider as a whole structure, it is consists of two elements and three nodes. Each node having two unknowns, therefore the total unknown is to be 6. Therefore your size of the stiffness matrix is 6. I top red color I indicates the unknowns. What are the unknowns? Node 1 V1 theta 1, then node 2 V2 theta 2, then node 3 V3 theta 3. The same way the column wise I indicates V1 theta 1, V2 theta 2, V3 theta 3. Then we have to assemble your global stiffness matrix based on equation 1 and 2. If you see that here, that V2 combination I mentioned as a 24. How we can get this 24 value? You look at equation 1 and 2. For equation 1, that V2 combination is a 12. The same way we go for equation 2. What is the combination of V2 it is a 12. Therefore 12 plus 12 24. The same way we have to assemble your global stiffness matrix. If you see that V2 combination is a minus 12, then how will get? If you see that equation 2 V2 combinations is to be minus 12. Well, go for equation number 1. There is no combination of V2. Therefore, it will minus 12 only. The same way we have to assemble, we will get your global stiffness matrix. Then we try to formulate a finite element equation. That means K times del into your force matrix. That means we know the stiffness matrix and also your displacement vector. Then we have to equal to your force matrix. That means F1, M1, F2, F2, then F3, M3. We just to look at your given structure. The one end is to be fixed. That means node 1 is to be fixed. It will offer reactive forces as well as movement. We initially assume the beam is axially rigid. Therefore, we need not worry about your axial displacement. That means horizontal displacement. It will subject to one vertical force that will be restrict the vertical movement of node 1, that is F1, and also a fixed support offers some movement. It will restrict the rotation of the structure at nodal location 1. Therefore, this F1, M1, it will the reactive force as well as movement due to supports. The one is fixed support. Then if you go for nodal location 2, it is subject to a roller support. It will offer one reactive forces that will be F2. Then this F2 2D, then M2 2D, that will be influenced by your uniformly distributed load. That means the distributed load as well as distributed moment. Because element 2 is subject to uniformly distributed load, this distributed load offers some nodal forces. That means F2 to 2D, then M2 2D, that will be a force as well as moment due to distributed load. The same way, the distributed load is a contribution some amount of nodal forces as well as nodal moments for location number 3, that will be F3D, M3D. Then and also location number 3, that will be having roller support. It will offer some reactive forces that will be indicates F3. That's why we calculate your distributed forces as well as distributed moments. How we can calculate the nodal force due to distributed load as well as nodal force due to distributed moment. The formula we already derived, F2DD, F3D is equal to QL by 2. Here the uniformly distributed load is subjected to in vertically downward direction. Therefore, we made a sign convention. If it is vertically downward, then it will consider as a negative. Therefore, F2DD, F3DD is QL by 2, where Q is a uniformly distributed load. That will be at 12 kilonewton. Therefore, 12,000 Newton into length of the beam is 1 meter divided by 2. We will get 6,000 Newton. That will be F2D. That will be minus 6,000 Newton. F3D also minus 6,000 Newton. This vertically downward distributed load, it will create a clockwise movement at location number 2, then anti-clockwise movement at location number 3. Therefore, we assume the clockwise movement is to be a negative sign, anti-clockwise movement is to be a positive sign. What is a bending moment due to distributed load? Node 2 and 3, the formula is QL square by 12, where Q is a uniformly distributed load. That means 12,000 Newton into meter is 1 meter, then divide by 12, we get 1000 Newton meter. The 1000 Newton meter is a bending moment due to distributed at a nodal location 2 is to be a minus 1000 Newton meter because it is a clockwise movement. Then location number 3, it is to be anti-clockwise movement, then it is to be considered as a positive sign. Then we have to apply into above equation. Then for nodal location F1, M1, it is a force as well as movement due to fixed support. Then roller support offers some reactive force, that will be F2. Then F2 DD value is a minus 6000 Newton. Then movement is M2D value is a minus 1000 Newton meter at nodal location 2. Similarly, the nodal location 3 also is to be having roller support. It will offer one vertical force. We assume in this positive direction F3 minus 6000 Newton, that is called as your nodal force due to distributed load. Then bending moment due to distributed load is 1000 Newton meter. We have to apply this above equation. Then we have, once you formulate a finite element equation, then we have to apply your essential boundary conditions. What are the essential boundary condition here? It means node 1 is to be fixed support. It will offer one react. We initially assume the beam is axially rigid. We need not worry about your horizontal displacement. Therefore, it will offer one vertical reactive force. It will restrict the lateral movement at nodal location 1. Therefore, V1 0, and also it will offer bending moment. That means M1 also is having some moment at nodal location 1. Therefore, your rotation theta 1 also 0. The same way, consider node 2. It will have a roller support. It will offer one vertical reactive forces. It will restrict that lateral displacement at location number 2. Same way, nodal 3 also subject to uniformly roller support. It will offer one vertical reactive force. It will restrict the movement. Then V3 also 0. Then we have to apply this above condition into your finite element equation. Then your finite element equation is modified into 8 into 10 power 5. We remove that respective rows and columns of your essential boundary condition wherever you apply. Then 8 to 4 theta 2 into theta 3 is equal to minus 1000. We will get two equation. From the two equation we solve, we have to find out theta 2 and theta 3 value. Where theta 2 is equal to minus 2.67 into 10 power minus 4 radians. Then theta 3 is equal to 4.46 into 10 power minus 4 radians. Then the second part of the question is we have to find out the vertical deflection at the midpoint of the distributed load. I already told that a safe function is a mathematical expression. It will helpful, or it will tell us how the field variable varies inside the element. So we know the displacement equation. Then V is equal to N1, that is not a V2, N1 V1 plus N2 theta 2 plus N3 V3 plus N4 theta 3. We know the value of N1, N2, N3, N4. Then we have to substitute the above equations. And also we already find out, sorry, here we just to look at here, this is a element number 2. Therefore we write in terms of your unknown coordinates of your element 2. Element 2 consists only node 2 and 3. Therefore the above equation is correct only. V is equal to N1 times of V2 plus N2 times of theta 2 plus N3 times V3 plus N4 times theta 3. Because we are talking about only the element number 2. Therefore, element number 2 is consist of node 2 and 3. Therefore, node 2 having only unknowns of P2, T2, the node 3 having V3, T3. Therefore, your displacement function can be written here in terms of only the unknowns of node 2 and 3 only. Therefore, the above equation is correct only. V is equal to N1 V2 plus N2 theta 2 plus N3 V3 plus N4 theta 3. Then we know the safe function value N2, N3 and N4 value. We have to substitute the above equation. This is N1, N2, N3, N4. We have to substitute X equal to 0.5 because the length of the beam is 1 meter. Our ultimate aim is we have to find out the vertical deflection at the midpoint of the your distributed load. Therefore, we have to substitute x equal to 0.5 meter. Instead of that, your V2 as well as V3 become zeros, because we already find out V2, V3 values to be 0, because the node 2 having roller support, it will offer one reactive forces. It will restrict the movement of V2, therefore V2 will be 0. The same way V3 also 0. It will offer one reactive forces that will restrict the lateral movement of node 3. V3 also 0. Therefore, above equation we substitute V2, V3 value 0 as well as x is equal to 0.5 meter. Finally, we arrive the vertical displacement at midpoint of the uniformly distributed load is V is equal to minus 8.913 into 10 power minus 5 meter. So once after watching this lecture, you can able to answer these following questions. One is, what is mean by beam? Beam is to be a horizontal structure member. It will carry a transverse loading. The transverse load means it will act perpendicular to the beam axis. It will resist your applied load by the combination of internal shear force as well as bending moment. This widely used as structural members. It will be classified based on the supports and conditions. What is the different types of beam? One is a cantilever beam, simply supported beam, overhang beam, then fixed beam and continuous beams. The first three beam is to be statically determinate structures. Another two beam is a statically indeterminate structures. Then derive the shape function for a beam element. We already derived that values v is equal to n1 v1 plus n2 theta 1 plus n3 v2 plus n4 theta 4 theta 2. Then question number 4, the beam element shown in figure is subject to a linearly varying load of maximum intensity Q0. Using the work equivalence approach to determine the nodal force and moments. We know that work equivalence approach, that means your nodal force due to distributed or distributed loads, maybe it is a UDL or UVL. F1Q is equal to 0 to L, your distributed load Q of X times your N1 into dx. Suppose if it is M1Q means this integral or 0 to L Q of X into N2 times dx. Similarly, F2Q is equal to 0 to L Q of X into N3 into dx. Then M2Q is equal to the integral of 0 to L Q of X into N4 into dx, where N1, N2, N3 is a shape function, is a function of X only. Therefore, then here the maximum intensity Q0 is equal to as a function of X, that value is here Q0 into X by L. Therefore, if this above integral equation, your Q of X can be replaced here Q0 into X by L, then your N1 times into dx, we will get the F1Q. That means your nodal force due to uniformly distributed load at lower location 1 and 2. The similar way we have to calculate F1Q, M1Q, then F2Q, then M2Q. Once if you calculate your distributed nodal forces and moments, then we have to arrange it in the matrix forms. Using the above result to calculate your deflection at node 1, if the problem is modeled into single finite element. Already we know that a finite element equation, that means your stiffness matrix into your nodal displacement vector equal to your force matrix. Then we have to apply this above equation, then we have to apply your essential boundary condition. Here the essential boundary condition is node 1 is to be fixed, therefore it will offer reactive forces as well as moments. Therefore, it will restrict your lateral displacement as well as rotation. Therefore, node 1, the boundary condition is V1 theta 1 equal to 0. Therefore, the unknown is V2 as well as theta 2. Then we remove the respective rows and columns of your finite element equation. That means V1 theta 1. Then we will get simplified finite element equation in terms of unknown V2 theta 2. Then we are solving this equation. Then finally we obtain V2 and theta 2. Thank you.